Hey, let's take a look here at section 6.4, logarithmic equations. So section 6.3, we had exponential equations where we had pretty much the same strategies here because, well, we should expect processes to be pretty similar because these things are inverses of each other, right? Exponents are inverses of logarithms. So we're going to be doing pretty much the same things. Here we have some steps for solving these. We're going to isolate the logarithm first. So we want either log base something of something equals some number, or we want to write it both sides as logs with the same base, right? Log base b of u equal log base b of w. So if we can write it like this, then we can equate the arguments there of the logarithms there. So whatever's in this position here, we can say that those things are equal. And again, this came from the fact that the logarithmic function was 1-to-1, and that implied that it had this is what 1-to-oneness means, right? If I have two function values that are the same, then their inputs have to be the same. Okay, so real quick, if we're in this case and we have like the logarithm equals some number, and maybe we can call it c, then we can rewrite it. Right, b to the c is equal to u, and then we can solve for u, right? So usually what we want to do is the thing with the stars here. We want to make it so that the logarithms have the same base on both sides. Or of course, maybe I'll rewrite this down here, rewrite the log equation as an exponential equation. So I think that our definition was written with y's and x's. Right, we can just rewrite with exponents instead of logarithms. So, okay, good. Let's just do this a few times. So, general strategy wise, we want to get the logarithm stuff alone, and ideally we want to have the same log base whatever on both sides. So we do have that in this case. So that means that I can equate the arguments. So log base 117 of this is equal to log base 117 of this. So those things have to be the same. Well, that tells us 1 minus 3x has to be x squared minus 3. And now we have tried and true methods to solve these, right? Quadratic equations are pretty quick to solve. We can just get everything on one side. So let's add 3x to both sides, and we can subtract 1 from both sides. And now we solve this guy by factoring, right? So what, x plus 4, x minus 1. Okay, so now we can say x is negative 4, or x equals 1. Something that we should have stated here, which would have been step 3, I think, is check for extraneous solutions. We remember what extraneous means, right? This means, well, extra. It's a solution that we come up with that's not actually a solution, so it doesn't actually work when we plug it in there. So we got to make sure that both of these are actually valid solutions. Well, what does that mean? We need whatever, maybe we can recall that the domain of y equal log base bx is everything that's bigger than 0, right? We can't remember the domain of a function is the range of its inverse. And remember the range of the inverse, which is the exponential function, was 0 to infinity, right? We couldn't get 0 and we couldn't get negative stuff. So the domain of our logarithm has to be the range of that exponential function. So anything that we put into the logarithmic function has to be bigger than or equal to 0. Well, long story short here is if we plug negative 4 in there, what happens? Well, we need 1 minus 3x to be bigger than 0. We also need x squared minus 3 to be bigger than 0. Now put in negative 4, see what happens, right? Maybe I'll put this in a different color. So if I put negative 4 in there, I'd have 1 minus 3 times negative 4. Well, that would be 13, and that is bigger than 0, so that worked. And if I put in negative 4 into this one, I would have negative 4 squared minus 3. So that's 16 minus 3 is 13. That's also bigger than 0. And we've just shown ourselves that it did work as a solution too, right? We plugged it in and we got 13 in both positions, didn't we? Well, we also have to check that it's true for our other solution. So 1. So 1 minus 3 times 1. Well, that is 1 minus 3 is negative 2. So no, that's not a solution, right? Because that's not bigger than 0. And we don't even really need to check this one, right? Because it's already doesn't work. So that's an extraneous solution. We would only say that our solution is x equal negative 4. And we're done. Okay, so yeah, check for extraneous solutions. We have to make sure that our answers are in the domain of the function, so that they're actually solutions. Okay, so let's do this one. Here we've got one logarithm here. We want to isolate it, right? That's our first step, is just to isolate that logarithm stuff. We want to get that piece alone. So to that end, we probably want to subtract 2 from both sides. So we get natural log negative. And then subtracting that 2 from both sides, 1 minus 2 would be negative 1. And now we can divide both sides or multiply by negative 1. So everything's positive now. Now I have one logarithm on one side and another logarithm on, or excuse me, I don't have a logarithm on the other side. I have a real number, right? Maybe it might help us if we rewrite that with a base, right? We know that when it's that ln, that natural log, our base is e, so that's 1. And now we have a log on one side and a real number on the other. We can just rewrite this with exponents. Okay, well, this is the power that we raise e to get x minus 1. Well, that means that e to the 1 would have to be x minus 1. And now we're pretty much finished, right? Just add 1 to both sides. So e plus 1 equals x, and there's your solution. And what we also should do is do the same thing we did on the other and just verify that we can plug that in there and that argument position is positive. So we need x minus 3 to be bigger than 0. Well, if we put e plus 1 in there, we want to know, is that true? Well, e, this is, I'm not sure exactly how much we've talked about this. This is e is a transcendental number. It's kind of like pi. It's a non-repeating, non-terminating decimal, and it's approximately 2.7, I think 18 something something something. But the point is, it's bigger than 2, so e plus 1 is bigger than 3, so that would mean this is a bigger than 0. So we would say yes, this is, and it's a valid solution. We can plug it in there, and it works. So yeah, how great. So yeah, it's somehow easier when we just have one logarithm on one side, right? Something that we could have done, real quick, something that we could have done here is we could rewrite 1 with a log base e, can't we? Like if I said that this side log base e, x minus 1, and I want to have log base e, then what would go in this position here? If I wanted this to be the power that I raise e to, I want a log base e of some number that's 1. So I want 1 to be the exponent that I raise e to get that number. Well, there it is, right? It's just e. And now we can say, well, x minus 1 equals e, and then we finish up x equals e plus 1. But we get to the same conclusion either way. I don't know, somehow rewriting a real number as a logarithm is sometimes uncomfortable. Like if this was a 2 instead, we could have rewritten that like that, you know. But I think we probably are better served by sticking with doing the thing that's easy, right? The thing that jumps out at you, and we should embrace that, right? All right, here we got another one. Okay, so we want to get all the logarithms on one side. Well, if we can, we want to write it with log base 7 on this side and 1 logarithm base 7 on the right hand side too. So we really could do that trick where I could say that 1 is log base 7 of 7. But but that might be a little more confusing than we want to make it. So what might be easier for us, and maybe we can do that maybe we can do that when we're done doing it this way. So what I would do here is I would put all the logarithm stuff on one side, and convenient things are going to happen, especially when we have the same base. All right, if I add that one to both sides, then we would have a plus log base 7, 3 minus x, and then 1 is left on the other side. Okay, well, now we know that we have a sum goes to a product, doesn't it? So I would have log base 7 and then the product of these things. So yeah, we're actually going to use these product and quotient rules we had in section 6.2, huh? Okay, good. Now we've got one logarithm on one side and a real number on the other. We can rewrite this with exponents. So we've got that log base 7 of that variable expression is equal to 1. So that means that 1 is the power that I raised 7 to get that number. And now it's got a familiar form. It's going to be a quadratic equation, and we can go ahead and solve this in the usual way. So let's go ahead and do that. We got a 7 on this side. That's not going to change, but we are going to multiply this polynomial out. So we got 1 times 3 and 1 times negative x. So I got 1 times 3 is 3. 1 times negative x is negative x. Then I've got negative 7x, right? Because I'm going to have negative 6 plus negative 1 would be negative 7. And then multiplying these guys together, we got plus 2x squared. All right. Maybe we can come up here and rearrange that. Sure. So subtracting the 7 from both sides and rearranging our terms. 3 minus 7 would be minus 4. Okay, now we want to factor this like we usually do. Hopefully this will factor. We got 2x and x. And then I want to multiply it so that I get a negative 7 in the middle. So I'm going to want a negative 4 there to give me negative 8, and then a positive 1 to give me plus 1 would be 7. Okay, good. So that's what we want. And from here, we can just jump right, probably just saying x equals negative 1/2. Don't know why I wrote a 3 there. Definitely said 1/2. Or x equal 4. And now we have to go back and we have to verify that these actually work, right? So if I'm going to do x equal negative 1/2, we can plug those into both of them. We could probably just eyeball it and see that we can plug it in and it goes in there, right? So if I put negative 1/2 in here, negative 2 times negative 1/2, that's going to be positive, so we're going to get a 2 in there. And we're going to get, positive number there as well. So those are both positive. That works just great. But if we put that 4 in there, the 4 is going to make that piece negative, right? 1 minus 8 is negative 7. So that's not going to work out with our 4. So we got to cross that out. So we only have one solution here, and it's negative 1/2. Happy days. Yeah, once we get the logarithm stuff away, then it's just smooth sailing, right? We've solved quadratic equations many times, and we will solve quadratic equations many more times in our future. Okay, great. Looks like we're going to be doing the same thing here, right? So our general strategy, again, is to get the log stuff alone. So let's put it all on one side. So we got log base 2, x plus 3, and then let's subtract this log base 2, 6 minus x. And that's equal 3. Alrighty. And now what? We've got a minus. So we've got a difference. And this is going to become a quotient. Right? This is our quotient rule. So we got log base 2, and then we got x plus 3 over 6 minus x plus 3. Okay, great. Now we have one logarithm, and we have a real number on the other side. And now we can rewrite with exponents. Okay, so this object is the exponent that we raised 2 to get the variable stuff. So that means 2 to the third power has to be equal to the variable stuff. And now we just solve this in the usual way, right? We know that 2 to the third, we know that that's 8. So we can just write it as 8. So as long as x is not 6, it is a legal move to multiply everything by 6 minus x. And so we do that. This is our general strategy with rational functions, right? We want to get rid of the fractions first and foremost is our goal. So now what? We've got that on the right-hand side. Those guys cancel out. I just have x plus 3 left over. And then on the right-hand side, what do we have? We've got 6 times 8 is 48 minus 8x. All right. And now we can take this over here and finish this up. So we want to combine all of our like terms. So 48 minus 3, that's 45. And then put the x's on the other side. Add 8 to both sides, right? 8x to both sides, you get 9x. So now this means x would be 45 over 9, which is equal to 5. All right, great. And now we would, go back in and we'd plug it back in and see if it works. So if I put in 5 into this one, 5 plus 3 is 8. And we can compute that directly, right? Log base 2 of 8, that's 3. And if I put 5 in here, that would be 1, right? So log base 2 of 1. So what's the power that you raise 2 to get 1? Well, it's 0. So 3 minus 0, that is 3. So it worked. So great, x equals 5. We can put a nice little box around it. And we're done. All right. Okay, one more here. Well, this one doesn't have the same base, does it? What should we do? Well, let's try to do what we usually do. So we want to get the logarithm stuff together. So let's slide that over to the other side here. So I would have 1 equals 2 log base 2 of x minus 2 log base 4 x plus 1. Okay, well, I know that these 2's are going to cause us problems, so why don't we just divide everything by 2? So if we divide everything by 2 on both sides, we get 1 over 2 equals log base 2 of x minus log base 4 x plus 1. Okay, so in order to combine these guys, we need the same base. So we need the same base to combine those. Well, we've got that nice change of base formula, right? So we can do that. 1/2 equal, if I want to write what would be easiest would be for a base of 2, right? Well, I can choose any base I want, say 2, and I can rewrite my logarithm. Recall the nice change of base formula. So yeah, recall the change of base formula. Okay, and with the green back, there it is. Okay, so now what? We can evaluate that thing. Well, log base 2 of 4, that's the power you raise 2 to get 4, so it's 2, right? So I got 1/2 equal log base 2 of x minus, now this thing is 2, right? That's a 2, so we got 1/2 log base 2 x plus 1. Okay, now we got them both the same base. That's super convenient. And now what? Well, we got this 1/2 in front of there, so we can tack that up as an exponent, right? Use that exponent rule. We got square root business. And now we can write that as a quotient. So we got 1/2 equals log base 2, and then there's our numerator, and our denominator is x plus 1 to the 1/2. Okay, cool. Now we have it as a logarithmic function on one side, and on the other side is just some number, and now we can rewrite it with exponents. So we have 2 to the 1/2 has to be x over x plus 1 to the 1/2. Okay, we'd probably be more comfortable looking at this with radicals, right, instead of exponents. We know that the raising something to the 1/2 power, that's a square root, right? We know this as exponent rules. Okay, so now what? We want to probably get rid of all the radical stuff. That might be a decent strategy. So if we square both sides, what happens? We got 2 on the left, and on the right-hand side, we got x squared over x plus 1. And now we can solve this in the usual way, right? Because all the radical stuff's gone, and we just have to deal with our denominator, and multiplying both sides by x plus 1 is going to make that go away. And we can do this provided that x can't be -1, right? And maybe right now we'll make a note, x can't be -1. Okay, so they cancel on that side. We've got 2x plus 2 equal x squared. So rearranging that, we've got 0 equals x squared minus 2x minus 2. And now we can go ahead and use our quadratic formula to solve this one. All right, so we've noted that we can't have x equal -1, so we can come up here and finish this out with the quadratic formula here, right? So when I have 0 equals my quadratic stuff, I know that I can say that x has to be -b, so that's going to be +2, plus or minus the square root of b squared, so that's 4, minus 4 times a, which is 1, times c, which is -2, over 2 times a. Okay, so I've got x equal, just simplifying this out, we got 2 plus or minus square root of, what is this, 4 plus 8 would be 12 over 2. And then we've got 2 plus or minus, reducing that radical, square root of 12 is 2 square roots of 3. And then we got 1 plus or minus the square root of 3. Okay, so now we're at the same spot we were at those last few problems, and we said, hey, I have to make sure that both of these things work. So we're saying that x equals 1 plus the square root of 3, or we're saying x is 1 minus the square root of 3. Now, something to notice here is that this one is positive. This one is negative, right? Because 1 minus square root of 3, well, square root of 3 is bigger than 1, so 1 minus something bigger than 1, well, it's negative, right? So we just have to remind ourselves what we had at the beginning, all the way back here. I have to have this thing, x plus 1, be bigger than 0, and we also have to have this thing be bigger than 0. Well, the negative one's not going to make that work, so we got to get rid of it. And the only solution here is our 1 plus square root of 3. And I mean, we could plug that back in up top, and we could rearrange this to show us that it's the same, like make the left side look like the right side. We can totally do that. And you probably should maybe leave that as an exercise for you to do, because every step of the way we want to verify that, am I doing the right thing? Is this correct? Am I clicking the button on submit? Is it actually right? We want to convince yourselves that it's correct without having the computer tell you it is. All right, so yeah, that's it for this section. I think the big deal, the moral of the story here, was when we had to discard those extraneous solutions. So be careful in this section, because we have to be a little more careful than we were with the exponential stuff, right? Exponential stuff, the domain was all the real numbers, but here it is not. Anyway, that's it for this section. So thanks for watching the video, and have a wonderful rest of your day.